Any questions about anything before we start talking about stuff? Questions? Okay. By the way, soon you'll have a new draft of the monograph available to you. I'm working on I'm trying to figure out how to use the LaTeX table of contents thing. So I've been carrying this book around with me everywhere I go. You know, like that is. And I just can't get this one thing to work. But as soon as I get that to work, you know, you'll have a new draft of the monograph that has some revisions, some typo corrections, and a table of contents. And it might be just a table of contents for the first half that I'll augment as we go along. But anyway, what have we been talking about? We've been talking about discrete time signals. And stuff you can do with them. And just to remind you, we have this notation F, R, or C. F to the Z, that's a set of all discrete time signals. It has a vector space structure. You can take linear combos, blah, 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 blah. And we had some various system properties. So algebraic, or signals properties. And when I'm talking about algebraic signals properties, I mean things like right-sided, left-sided, finite duration. So finite duration is like the classic one of those. And last time we spent the majority of the class talking about these analytical signals properties. And we had bounded signals, absolutely summable signals, and square summable signals we talked about, and notation for the set of all such things. All bounded signals is L infinity, all summable signals, absolutely summable signals is L1, all square summable signals is L2. And we noticed that some of the sets of signals having these various properties are actually subspaces of F to the Z. They're closed under linear combo, and they're closed under time shifting. And those are good things to know. And I forgot, time shifting is also something we talked about. And we talked about various subspaces, not just subsets, of F to the Z. Okay, and at the end of class last time we defined convolution. And that's where I want to pick it up today. And you all saw convolution, no matter who you took EC 2200 from, you saw convolution. Discrete time convolution. Those of you who maybe didn't take EC 2200, you applied physics people or CS people, you might have seen it somewhere else. I don't know. But what's the difference in this class in the way we treat convolution from the way we treated it in 2200? The difference is that we're going to sweat a lot more of the details. We're going to worry about, say, when is the convolution of two signals well defined? When does it exist? When doesn't it exist? And how does it relate to these various algebraic and analytical properties of the signals? Those are things we sort of swept under the rug in 2200. Okay, but the definition is the same. So, convolution. If you're given x1 and x2 in F to the Z, and remember we're using just the letter to denote the signal, not x1 of n, x2 of n, their convolution, if it exists, is the signal x1 convolved with x2 specified by the following formula. And whenever we say specified by, we mean we need an expression that tells us what that signal is at every time n. And the expression for x1 convolved with x2 of n is this. x1 convolved with x2 of n. And again, this is the whole signal. And of n is its value at time n, is the sum from k equals minus infinity to infinity of x1 of k, x2 of n minus k. And that's true for all n. We noted that it doesn't matter where you put the k and where you put the n minus k. So we saw last time that this is the same as if I did this. Sum from k equals minus infinity to infinity. Put the n minus k with the x1 and the k with the x2. All right, so that's pretty much where we're at with convolution. This is familiar to everybody, right? You've seen this before, even if you haven't worried about what's under the hood, so to speak. Okay, so some easy properties of convolution. First of all, and remember we can interpret that equivalence of the upper and lower expressions in some sense as being that convolution is commutative, if you want to get fancy about it. But it's also associative in the sense that if I take the convolution of x1 with, and you can use convolution with, convolution of that with another thing, or convolution of x1 and x2. I'm going to be using all these expressions interchangeably, and this issue came up pre-class today, linguistic issue. Like, the verb is convolve. You convolve two signals. You don't convolute two signals, right? But, like, if we're using it in the colloquial sense, like, wow, that class, his explanation was so convoluted. You know, we don't say, his explanation was so convolved. You never would hear that, right? So why do we say, why is the verb convolved, but when we're talking in a disparaging manner about someone's lousy presentation, we say convoluted? I don't know the answer to that question. But in any event, if I take x1 and I convolve it with the convolution of x2 with x3, I get the same thing as if I'd convolve x1 with x2 first, and then convolve that signal with x3. And this is true for all x1, x2, x3 in f to the z, for which all the indicated convolutions exist. Okay, so sometimes that saves you time. One of them might be easier to do than the other. Another thing, and I'm not going to prove these in class. They're really easy. It's just a matter of going through a bunch of sums, and the proofs are in the monograph, so I'll let you look at those if you want more detail. It's also what we call bilinear in the following sense. In the sense that if you take, say, a signal x1 and you convolve it with a linear combo of x2 and x3, and I always get the indices here messed up. I'm trying to be cool the way I index things. And by trying to be cool, you always mess up. So this is equal to C2 x1 convolved with x2 plus C3 x1 convolved with x3. And also, if I do it the other way around, like I take C1 x1 plus C2 x2 and convolve that with x3, I get C1 x1 with x3 plus C2 x2 with x3. And this is for all C1, C2, C3 in F, and all x1, x2, x3 in F to the Z, for which the indicated convolutions exist. Okay, so those are the easy properties of convolution, and they're very simple to show. You can just sort of visualize it in your head why the bilinear one holds, just because of the kind of massive linearity that leaps out of the page at you when you look at the expression for convolution. The associative one, that's a little harder, because you've got sums running over K and over L, and you have to interchange orders and whatever. But proofs are in the monograph, as I said before. And maybe write that down just to remind you. And they're easy. Okay, so now let's start biting the bullet on existence. Like, what are some criteria for the existence of convolutions? Before we do that, I want to note one really important special case. And this is something we emphasize somewhat in EC 2200. And that is the following. So here's an observation. For every x in f to the z, if I take the convolution of x with a delta, with a discrete time impulse, delta convolve with x, what do I get? X. In other words, if you convolve delta with anything, any signal at all, the convolution is guaranteed to exist, and bonus, it actually equals the signal you started with. So in particular, delta convolve with x exists, and the interpretation of this is that quote-unquote delta is an identity element for discrete time convolution. Just as 1 is an identity element for multiplication of real integers, whatever, rationals, 0 is an identity element for addition, delta is an identity element for convolution. Convolution is just like any other operation that you would do on two things. It just happens to be a little more complicated. Now, why is that the case? Let's just write it out and see. See this? By definition of convolution, if I take delta given x in f to the z, delta convolve with x at time n is the sum over all k, delta of k, x of n minus k. And that's true for all n. An ostensibly infinite sum, right? But how many terms in it are actually non-zero at most? What is delta equal to? Delta, Ricardo?
It's going to be 0 for all cases with k is 0.
Yes. Delta of k is 0 for all k values except when k equals 0, which means that infinity minus 1 of the terms in this sum are zeros. And the k equals 0 term is the only one that maybe is non-zero. And it depends on what x of n is. So this is the same as dot, dot, dot. 0 plus 0 plus 0 plus delta of 0, which is 1, times x of n minus 0 plus 0 plus 0 plus 0 plus dot, dot, dot. And that's true for all n. And that equals x of n. So delta convolved with x at time n is equal to x at time n for all n, and that's the same as saying delta convolved with x equals x. Just to get you used to using this signal as just one letter notation. I know it could be beating a dead horse for some of you, but I know that there's some folks in the class who struggle with getting used to this, so I want to emphasize it. Thus, delta convolved with x at time n is equal to x at time n for all n, which is the same as saying that delta convolved with x equals x. Alrighty. So that's a good thing to know. We have an identity element for this operation of convolution, and it's a particularly simple signal. It's kind of the ultimate finite duration signal, or penultimate finite duration signal. 0 is, I would say, the ultimate one. Okay, any questions about that argument? It's pretty simple, but I just want to make sure we're on the same page. Or same board panel? I don't know. All right. So here's a question. How can we tell, so when does x1 convolve with x2 exist? And the answer is, the first part of the answer is not always. And before we go through listing criteria for existence of convolution, I probably ought to give you an example where the convolution doesn't exist, right? It's only fair. Now, can anyone just think up quickly an example of two signals x1 and x2 that are particularly simple, whose convolution fails to exist? Alex.
X1 equals x2 equals 1 for all n.
Yeah, that's a really simple example. So here's an example. Suppose you take two non-zero constant signals. And I'm going to take Alex's example and embellish it in my style, okay? So how about x1 is the signal with specification x1 of n is equal to 7 for all n. And x2 has specification x2 of n equals, say, 13 for all n. That's similar to Alex's example. If I try to compute the convolution of x1 with x2, what happens? So try to find x1 convolved with x2 of n. By definition, that would have to be the sum over all k, x1 of k, x2 of n minus k, which is equal to the sum over all k of 91, which is 7 times 13, which is infinity times 91, which is not a number. So bottom line is, you cannot compute the convolution of x1 with x2 of n. The infinite sum defining x1 convolved with x2 of n fails to converge for any n. And you don't even have to use constant signals. You could use one being a unit step and the other being a constant, or one being a unit step and one being a time reverse unit step. There's tons of examples where the convolution fails to exist. So, when does it exist? What I'm going to do in what follows today is give you a non-exhaustive list of sufficient conditions for the existence of x1 with x convolved with x2. Now let me explain what I mean by non-exhaustive. And what I mean by sufficient conditions for the existence of x1 convolved with x2. And this is something we never worried about in 2200, but we are worrying about in this class. What do I mean by sufficient conditions? I mean that if x1 and x2 satisfy these conditions, then their convolution exists. That's what I mean. What I mean by non-exhaustive is that there are pairs of signals that fail to satisfy any of these whose convolution still exists. And I'll give you an example of one of those when we're done. All right. So, first issue to notice, what is the key thing that militates against the existence of the convolution of two signals when it doesn't exist? It's the fact that to compute a convolution, you have to sum up an infinite sum. And the existence of a given infinite sum is not a given. Okay? Only infinite sums with certain properties exist. So that's the whole key to non-existence when non-existence is what's happening. And the first two criteria essentially get rid of that problem. Okay, so first note, what makes x1 convolved with x2 fail to exist is failure of one or more infinite sums to converge. The first two criteria, the first two sets of sufficient conditions for existence, get rid of this problem. And you'll see how. So the first two existence criteria get rid of this problem. Okay, so what's the first one? The first one, criterion, I'm going to number them 1, 2, 3, 4, 5. And actually in the version of the monograph you have now, there's only 4 criteria, but I've added a new one this year. And that's in the revised version of this chapter. So you'll be seeing that come up. I'll tell you what it is when we get to it. So criterion 1 goes like this. If either x1 or x2 or both has finite duration, then x1 convolved with x2 exists automatically. And furthermore, it has finite duration if both x1 and x2 do. So if someone comes up to you in Hope Plaza and says, I have this signal x, and I'm worried about convolving it with some other stuff. And since you're an ECE, you can tell me whether I need to worry and what signals I have to avoid. Okay, show me the signal, you say, and she says, or he says, or whoever, here it is, and it's a finite duration signal. What do you say back to them? No worries. You can convolve that signal with anything. Okay? And that's going to be a theme that we're going to see again and again and again. Finite duration signals can be convolved with anything, with no worry about existence. Okay, so how does this go? Let's see. I said that the way these first two criteria shake out is infinite sums go away as a problem. So let's suppose, to start with, let's suppose that x1 is the one that's a finite duration signal. So say x1 has finite duration, and let's be specific. Say that x1 of n is equal to 0 when n is less than, say, capital N1, and x2 of n, or n x1 of n, is also equal to 0 when n is bigger than capital N2. Let's see what happens when we compute x1 convolved with x2 for any x2. So for any x2 in f to the z, x1 convolved with x2 at a time n, it's going to be the ostensibly infinite sum from k equals minus infinity to infinity of x1 of k, x2 of n minus k. And up there on the top board, we saw a kind of a microcosm of this situation. And I noticed the video note guy just turned the camera up to the top board. Thank you. We had an ostensibly infinite sum that had only one term in it that was possibly non-zero. What about this ostensibly infinite sum? Anybody propose what we can do to this to turn it into an unproblem? Someone who doesn't say anything, usually? How about? Okay.
Except the lower bounds at N2 and the upbounded.
I would probably do it the other way around, but you got the right idea. X of n is 0 to the left of n1 and 0 to the right of n2. And what's your name, by the way?
Ian.
Ian?
Yeah.
Okay. So now there's 2 Ians at least in the class. We have 3 Alexes, or 4 now. I discovered another Alex. There's only one Nathan. Yes, you're right. There's a Steven and a Steve, okay, but I don't know if there's any other Stevens or Steves. Anyway, okay. There's 2 Davids out there and one up here. What's that? 3 if you count me, yeah. Okay. All right, well, Ian was right. What you do is you chop the lower limit off at n1 and the upper limit off at n2 because x1 is 0 for k values that aren't between n1 and n2. And this is a finite sum, and it exists for all n. So, bottom line, x1 has finite duration. The infinite sum convergence problem goes away. And of course, the same thing would happen if we had x2 had finite duration, and proving that if x1 and x2 both have finite duration is just an exercise in indices, and I don't like doing that on the board, so I'll let you look at the monograph for that. So, same argument works when x1 is arbitrary and x2 has finite duration. And proving that the convolution also has finite duration when both do. Is easy but boring. So once again, I'm going to punt that one to the monograph. Okay. To give you a rough idea of how it goes, if you think about the duration intervals of x1 and x2 as being these bounded intervals of integers, and you think of what's happening in the convolution sum, you can think of one of those duration intervals sliding across the other one. And when they're intersecting is when you have a non-zero thing. When they're not intersecting is when you have a zero thing. So that's how it works out, but you have to turn that into a math argument. You have to turn it into an N1, N2, M1, M2 kind of thing. And I think it's easy, but it's boring. Nonetheless, intuition you get from that, and this is something I'm going to try to help you develop on the homework, is that when you have two signals that have a given duration interval, then in general their convolution is going to have a duration interval that's kind of like the concatenation of those, or the length of it is going to be around the sum of those. Okay. Now here's an interesting question that a version of it will appear on the prelim, I'm sure. Suppose I have two signals x1 and x2, and I convolve them, and I get a finite duration signal. Does x1, do both of them have to be finite duration? Does one of them have to be finite duration at least? Or is it possible to take two infinite duration signals, convolve them, and get a finite duration signal? What do you think? I think it's a hard question. I wouldn't know a way to sort of intuit my way to that question. I would have to play around with a bunch of signals. Varun?
You have signals that are odd, not strange, like mathematically odd. You could have a situation where
It's x of n equals minus x of minus n equals minus x.
I'm just trying to think, like, if you have one signal that's even and one signal that's odd, you could have for the first set of you could have something with negative area and eventually that positive area.
Yeah, things like that happen. Basically, it turns out it's not exactly that, but it's similar to that. You can have things like it's a long story, but I don't even know why I brought that up. It distracts us from criterion 1, criterion 2. Ricardo?
I mean, couldn't we just point to criterion 1?
It's a sufficient condition. It's not a necessary condition. If x1 or x2 has finite duration, then their convolution exists. If they both have finite duration, then their convolution has finite duration. It doesn't say that if the convolution of two signals has finite duration, then at least one of them does. Okay? Yeah. Yeah, these are one-way streets, these criteria. They are non-exhaustive, and they are only sufficient. Okay, criterion 2. If x1, let's state it this way. If x1 and x2 are either both right-sided or both left-sided, then their convolution exists. X1 convolved with x2 exists and has the same sidedness as x1 and x2 share. So if x1 and x2 are both right-sided, then their convolution exists and is also a right-sided signal. This is something we kind of implicitly used a lot in EC 2200, at least last semester, because we were dealing most of the time with signals that started off at time 0. So we never had to worry about the existence of convolutions because everything was causal and everything started off at time 0. So we were always under this criterion 2 umbrella of comfort, so to speak. Okay, now I promised you that both of the first two criteria made the infinite sum problem go away. How does that happen here? So suppose for specificity that they're both left-sided, both right-sided. For some reason, I find this proof a lot easier to do with right-sided than left-sided. I don't know why. I guess it's probably a handedness, brainedness kind of thing, but anyway. And suppose specifically that x1 of n is 0 for n less than capital N1, and x2 of n is equal to 0 for n less than capital M1. So they both have on times. They might be different. Like x1 might turn on at time 0, x2 might turn on at time minus 10 to the 59th. Who knows? So let's try to figure out x1 convolved with x2 of n. Again, we start off with the standard, ostensibly infinite in both directions sum, x1 of k, x2 of n minus k, right? And the first step we can take is use the fact that x1 doesn't turn on until time k equals n1. And we get the sum from k equals n1 to infinity. x1 of k, x2 of n minus k. And that's true for all n. And this is because x1 is 0 when k is less than n1. So let me write down that reason. So that's because x1 of k is equal to 0 when k is less than n1. Okay, now we invoke the x2 not turning on until its argument is equal to m1. And this is a little tricky because we don't have just a k inside the x2 under the sum. We have an n minus k. So we're going to have to play around a little bit. So meanwhile, x2 of n minus k equals 0 when n minus k is less than m1, which is the same as saying when k is bigger than n minus m1. What does that mean? That means that the upper limit of the sum is not really infinity, ever, for any value of n. The k values above n minus m1 give x2 of n minus k equals 0, so the sum tops off at most at n minus m1. But it turns out it's a little more subtle. So let me break this up into two cases. It's the sum from k equals n1 to n minus m1, x1 of k, x2 of n minus k, when n minus m1 is bigger than or equal to n1. That is to say, n bigger than or equal to n1 plus m1. What if n minus m1 is less than n1? What happens then? What do I have to fill in that blank with? Think about it. This sum, defining x1 and x2, x1 convolved with x2 of n, is a sum over all k values that start with k equals capital N1. And then they go up until x2 turns off, and that is little n minus capital M1. But what if little n minus capital M1 never even happens above k equals capital N1? There are no terms in that sum. Okay? So this is 0 when n minus M1 is less than N1. This is the same as saying n less than N1 plus M1. And in one fell swoop, what does this show? This shows that the convolution exists because it's always given by a finite sum when it's non-zero, and it's right-sided because it's 0 before time N1 plus M1. Now let me just pull that apart a little bit. Make sure you get it. This breaking up into cases thing happens a lot when you're doing convolutions, and I'll go through a couple examples. And there's more in the monograph. But for now, so let me just wrap up the theorem and then try to pull it apart and explain it a little bit. Thus, x1 convolved with xn, x2 of n, or x1 convolved with x2 exists because when non-zero, it's given by a finite sum. Namely that top term there, and is right-sided. Because it's 0, x1 convolved with x2 of n is 0 when n is less than n1 plus m1. And that proves the result. And a similar argument works for left-sided. Now let's look carefully at that breaking into cases. So the idea of the sort of two-case specification of x1 convolved with x2 of n is as follows. First part is that when n is n minus m1 is bigger than n1, the sum goes from k equals n1 to k equals n minus m1. Because x2 turns off when k hits n minus m1. Specifically, x2 of n minus k turns off when, I'll put that in quotes, k passes n minus m1. That's the top case. When n minus m1 is less than capital N1, sadly, so when n minus m1 is less than the bottom limit over there, capital N1, then sadly, x2 of n minus k never has a chance to be non-zero over the range of summation n1 to infinity. So x2 of n minus k, its interval of non-zeroness is helplessly to the left of the interval of summation there. So never, quote unquote, gets to be non-zero over the summation range cap n1 less than or equal to k less than infinity. Thus, 0 arises. Okay, now, that's how the case breakdown occurs. This happens a lot when you're doing convolutions. So you've got to get used to that. And often for me, I have to write out these explanations for myself, just to convince myself they're true. I don't have a good quickie mnemonic for doing these. Some people do, and more power to you if you're one of those. But does this make sense? Do you get this? You had to do some of this last year, no matter who you took 2200 from, I'm sure. Computing convolutions of right-sided signals with each other. Right? Yeah. Well, I know you did it. But the people who took it from Dorshak or Langtong or whoever, Suhan, did anyone take it from Suhan? Okay, how many people took it from Peter Dorshak? So you were like the fall last year. We had some of the same TAs in the spring. We had Jesse and Ashkan and I'm blanking on his name. Ramiz, yes, the guy who knows Hindi, right, right. And so you all did this. You all did this at some point in your lives, I'm sure. Okay, well, stare at that for a couple of minutes, take the 3-minute break, and then we'll do the other criteria. No, he took a job at a company in the Syracuse area. He graduated. Ashkan is still at Cornell. He's doing a 3-semester MEng, and Ramiz also graduated. I got a good picture with them at graduation in their caps and gowns and stuff. So. They were my 2 favorite TAs. So. The other guy, Lang student, Jalin. Jalin Liu. He was a really good TA, but he was coldly efficient. You give him papers to grade, they come back the next day, that kind of thing. But he wasn't as sort of fun as Jesse and Ramit. So. Now wait, you had the Ramiz or the Ashkan lab, right? And he was the one who was clueless about whether we were having a lab a given week. And I'd send out these emails, no lab this week or lab this week, and then the day of the lab, he would send me an email like, "Do we have lab today?" Or worse yet, "I'm at the lab now and there are no students here. What's up? We don't have lab this week." Or
he would go the weeks that we didn't have.
Well, you were the one who emailed me the first. We're waiting for the TA, right? Right.
I'm sorry.
It was kind of embarrassing. I think he just had he was really deeply involved in his MEng project. And yeah, well, Jesse was very conscientious. Okay. So anyway, this is important. This splitting into cases thing happens a lot. Important. All right. So now the rest of the criteria. The rest of the criteria for convolution existence involve the analytical properties of signals rather than their algebraic properties. What's on your tablet, Alex? What's going on there? Yeah. Notes? Cool. Okay. Yeah, it was funny. One year my sister was recruiting at career fair and she came to class and there were these two guys who sat back there in, about where you are, and they were always like kind of whispering to each other and doing stuff on their laptops, and it doesn't bother me, whatever. And my sister was up there and she said, I didn't know what those guys over there were doing. And so this went on the whole semester. And like 2 weeks before school ended, one of the people in the class came down with mono, and so she was like laid up for the rest of the semester, and so she couldn't come to class. And so I sent out this email to the whole class, hey, so-and-so, or one of the students has mono and she can't come to class. Does anyone have notes that they wouldn't mind giving her a copy of? I'd really appreciate it if anybody has some good notes. And those guys sent me an email and said, we have everything electronically. We've been like doing it in LaTeX the whole semester. So I thought, how cool. So I emailed my sister and I told her that that's what they were doing. Anyway, okay, so now we know Alex is doing it too. Criterion 3. Okay, so this has to do with the analytical properties, like I said. Okay, and it goes like this. If one of the signals is a bounded signal, so if one of the signals x1 and x2 is bounded, and remember our notation for that, that is to say an L infinity signal, and the other is absolutely summable, and the notation for that is an L1 signal, then the convolution exists and is a bounded signal. Moreover, we can actually get an upper bound on the infinity norm of this bounded signal. The infinity norm, remember, is the soup of all its values. x1 convolve with x2 infinity norm is at most equal to the product of the one norm of the L1 signal, whichever one that is, with the infinity norm of the L infinity signal, whichever one that is. Okay, now let's do a little reality check here. Remember the classic example we had that Alex brought up of two signals whose convolution was not well defined. The constant signal 1 for both. Those are both bounded signals. Their convolution is not well defined. What makes it fail is that neither of them is absolutely summable. That's essentially what's going on there. Absolutely summable things have to be bounded, but the other way around is not necessarily true. Okay, so it turns out this criterion is at the heart of what's called bounded input, bounded output stability for LTI systems, which we'll get to as we go along. And for the detailed proof, I refer you to the monograph, but here's the idea of the proof. Just to show you what's going on. Let's, for definiteness, let's let x1 be the L1 signal and x2 be the L infinity signal. So say x1 is in L1 and x2 is in L infinity. So x1 is absolutely summable, x2 is bounded. Let's try to compute x1 convolved with x2 of n. And let me put absolute value signs around that, just for the heck of it. That's equal to the actually, not just ostensibly anymore, infinite sum k equals minus infinity to infinity, x1 of k, x2 of n minus k. And everybody knows that the absolute value of a sum is bounded from above by the sum of the absolute values. And here's where I'm being undetailed because I'm doing it with an infinite sum instead of a finite sum. So this is less than or equal to the sum from k equals minus infinity to infinity of absolute value of x1 of k times the absolute value of x2 of n minus k. But x2 is a bounded signal, so we know for all k, absolute value of x2 of n minus k is less than or equal to the infinity norm of x2. Because the infinity norm of x2 is just the soup of all of its values, absolute values. So this whole thing is less than or equal to sum from k equals minus infinity to infinity of x1 of k absolute value, all that times x2 infinity norm. And what's the expression in the parentheses? Yes?
The one norm of x.
Yeah, the one norm of x1. x1, one norm, times x2 infinity norm. So what we've shown is, we've shown that for every n value, x1 convolved with x2 of n not only exists, but also is bounded from above in absolute value by x1 infinity, x2 infinity. So thus, x1 convolved with x2 of n exists and satisfies x1 convolved with x2 exists and satisfies absolute value of x1 convolved with x2 at time n is less than or equal to x1 one norm times x2 infinity norm for all n, meaning that x1 convolved with x2 itself is a bounded signal. It's an L infinity, and its infinity norm satisfies the indicated inequality. All right. So that's a criterion that depends on the analytical properties of x1 and x2. David.
Just had a question. So we're looking at the two different sort of, I guess, axes of signals. Like we determine what you can prove it. There's a convolution. We're looking at it finite duration. You can also prove that it's convolution. We're looking at it by its boundary, right? So What's there to stop a finite duration signal from having like an infinite or unbounded state, and then you can't actually sum it because it's infinite?
Okay, his question basically is there any such thing as an unbounded finite duration signal?
I get further.
No, that's really what your question boils down to, right?
But
In discrete time, no. But to think about this one in continuous time, like you could have like 1 over x going out to here, right? And then define it to be 0 at 0. That's a finite duration signal, but it's unbounded. In discrete time, you can't have that because the set of values of a finite duration discrete time signals is a finite set. And there ain't no way to have a sequence of those going off to infinity. Right? Now, in continuous time, we get rid of signals like this. We assume away signals that are unbounded on bounded intervals. And we'll get to that in a couple weeks. Anyway. All right. So anyway, this is the first criterion based on analytical. The next one is not in your version of the monograph, but it's in the one that you're going to get soon, criterion 4. If x1 and x2 are both square integrable signals, that is to say, L2 signals, then the convolution of x1 with x2 is well defined. It exists. And is also a bounded signal. And you can put an upper bound on its infinity norm, and in the monograph, the new chapter of the monograph where it does this, I give you an upper bound that we're going to improve on later in the course when we talk about Hilbert spaces and stuff. So in fact, its infinity norm its sup over all n is less than or equal to 1/2 times the sum of the squares of the two norms of x1 and x2. And later we're going to improve on this bound. So we can tighten this bound. But this is so easy to derive, I figured I'd derive that one first. So I'll tell you the key. If you want to look up in the monograph the key thing that we use to tighten the bound, it's called the Schwartz of Equality. And we encounter that when we talk about the Hilbert space orthogonal expansion approach to doing Fourier series. And I'm not going to do any proving of this in class. It's a quickie. Leave it for the monograph. Final criterion 5. If x1 and x2 are both absolutely summable, square summable is what I meant to say there, not integrable. Did anybody notice that?
Wait, is it interchangeable? Can you say it both ways?
Integrable and summable?
Yeah.
No, summable is what we use in discrete time. Integrable is what we use in continuous time. And I was just getting like 3 weeks ahead of myself there. So if x1 and x2 are both square summable signals, then their convolution exists, it's bounded, its infinity norm has that upper bound, upon which we can improve and will. All right, final criterion. If x1 and x2 are both absolutely summable, that is to say L1 signals, then x1 convolved with x2 exists. And furthermore, it's also an L1 signal. It's also absolutely summable. And a fancy mathematical way of saying this is that the vector space L1 of absolutely summable signals is closed under convolution. It's a convolution algebra, whatever. You know, some people, that's math speak for what's going on here. Okay, so that's the last criterion. Again, I'm not going to give any proof for that one for today. You could read about it in the monograph if you want. So proofs of the last two are in the monograph. But let me just ask you a quick question. A quick question here. Remember, okay, so proofs of criteria. Four and 5 in monograph. They're not hard, but I don't see the sense of wasting class time on them or using class time on them. Let's put it that way. Remember, we had this chain of stuff. Like, if you're absolutely summable, then you have to be square summable. If you're either absolutely or square summable, then you have to be bounded. This is all true in discrete time. It's not necessarily true in continuous time. In criterion 5, how do I know right away, given the previous criteria, that x1 convolved with x2 exists? Zach.
Because from, I think it was the first one, maybe the second, one of them's bounded, one of them's absolutely summable.
Yeah, it's actually the third one. Yeah, it's lower right. Yeah. Because by criterion 3, if you have an absolutely summable signal and a bounded signal, their convolution has to exist and be bounded. Well, if they're both absolutely summable, then they're both also bounded. So you have the situation of an absolutely summable and a bounded going together. But it's not just that their convolution is bounded. It is now not only bounded, but absolutely summable. That's what the additional strength of that gives you. Now, you can't quite do criterion 4 that way, because being square summable doesn't imply that you're summable. See, it's the other way around. So you can't use criterion 3 to prove existence in criterion 4. You have to sort of do it by hand. But it's worth like seeing how you can get pieces of the higher criteria from the earlier ones sometimes. All right. So I promised you that what? What's so funny, Ricardo?
404, and that's error.
Get out.
It's 404 and what? Oh, page not found? Is that what you're talking about? Oh. So, see, 404 is like the computer science nerds version of 420, right?
I think for them 420 is just 420.
420 is 420 for everybody. All right. Okay. All right. Anyway, I promised you. I promised you that I would not let you leave. Well, no. I promised you. I promised you that these criteria were non-exhaustive. They may be exhausting, but they're not exhaustive. Why? What does that mean? So, note. These are only sufficient conditions, and criteria 1 through 5 are not exhaustive. That is to say, there exist pairs of signals. So there exist x1, x2 pairs, satisfying none of the criteria for which x1 convolved with x2 exists. And let's see if anyone's clever enough just to come up with one. I have practice doing this, so. So the bottom line is they can't both be right-sided or both left-sided. Neither of them can be finite duration. They can't be an L1 and a bounded, or two L2s or two L1s. David? That convolution doesn't exist as it happens. Step function and a reverse step function was a really good idea, okay? But slightly wrong. Okay, Manish.
Step function and then a step function going the other way, but also inverted.
What do you mean, but also inverted?
Like, you know, positive one here, that side.
That convolution doesn't exist either. Okay, he proposed u of n and minus u of minus n. Okay, not quite. It doesn't happen. It doesn't exist. Convolution doesn't exist. Jusung. I'm going to call you by your Korean name.
Monotonically increasing and decreasing.
Monotonically increasing and decreasing. Nice words, but I'm not sure how they fit together.
I'm just taking a shot at it.
No, there's this famous line in the old Dick Van Dyke Show where Carl Reiner's playing this artist. He said, the guy's stumbling when talking to him. He says, "Go on, that was a very good sentence." You know, so that's what I felt like saying to you.
I'm just like, you know,
All right, let's see what Zach's idea is, and then I'll show you. It's a bad idea? You gave up? What about you?
Step function, reverse step function, but then
Exponentially decaying in which direction?
right-sided one.
Okay, well, in that case, you have a right-sided and a right-sided, I think.
And one less. The mirror.
Okay, that will actually work. And the example I'm going to give you is sort of similar to that, but it's a little bit simpler. Okay, so here's an example. One of them is a step function. Okay, so each of you was half right. Okay, no, except you. That makes you unique. X2 has specification. X2 of n equals 7 to the n for all n. Okay, so let's make sure we agree that this does not satisfy any of the criteria. Neither of the signals is finite duration, so criteria 1 is out. Criterion 2, x1 is right-sided, x2 isn't even sided. So that doesn't work. Criterion 3, x1 is bounded, but x2 is far from being L1. You can't sum that signal. You can't sum up 7 to the n over all n. So that doesn't work. And similarly, criterion 5 is ruled out because neither of them is L1 and neither of them is L2 either. So criterion 4 is out. So this satisfies none of the criteria, but we can do the summation to get x1 convolved with x2 of n. Sum from k equals minus infinity to infinity, x1 of k, x2 of n minus k. x1 of k is 1 for k bigger than or equals 0, 0 for k less than 0. So this becomes a sum from k equals 0 to infinity of 7 to the n minus k, because that's what x2 of n minus k is for all n and k. And this is just 7 to the n times the sum from k equals 0 to infinity, 7 to the minus k. So that's 7 to the n over 1 minus 1/7 by geometric series, which is what? 7 to the n plus 1 over 6 for all n. think. So that's an example where the convolution exists, but the signals don't satisfy any of the 5 criteria. And the reason this is similar to the one you proposed, all I did was instead of chopping off the 7 to the n at n equals 0 and having it go to the left, I let it go for all time in both directions. Okay, so we'll continue this next time, but we're pretty much done with this, and we're going to start talking about systems. So.